talking to us about Chern-Simons theory.
Right.
Welcome to Jyotirmoy. Thanks for coming here and giving us a talk.
Well, it's a real pleasure to be in TIFR. It's very, very nostalgic and at the same time very inspiring. So thanks a lot to the string theory group and Puni in particular for the invitation. So today I'll be talking about a paper which we wrote last December. So this is work done with Shiroman, Tarun, both of them I think most of the audience knows very well, and there is Aditya, who is my student. He did much of the heavy lifting in this project, and there's Anurag, who is an undergrad in IIT Kharagpur. So this is the work which I'll be talking about. It's about Chern-Simons theories, but I think many people in the audience were already in the Lodha meeting, and I think you've heard Tarun speak about this work. But it was a small meeting, so hopefully I'll tell you things which you haven't heard about before. Slightly more detailed. Okay, so it's just an expanded version of that talk. So this whole thing is, in some sense, started a long time ago. So just to motivate, where we come from, why we kind of went into this kind of thing, is that we wanted to understand Chern-Simons theories in AdS space. Okay, so the idea is that, of course, here there are experts. Many people here have worked on Chern-Simons theories in flat space and discovered, particularly Chern-Simons theories, when you put matter in it, it has various interesting features, including dualities, including interesting facts about scattering matrices, which were discovered. And so all of that is true in flat space. And I want to ask the question that, what happens to these quantities in AdS? You might think that there's a trivial generalization, but AdS comes with a boundary. Okay. So the main focus is to understand the boundary conformal data and the implications of these exotic stuff that happens with Chern-Simons matter theories on the boundary data. That was the main goal. And I think we started thinking about this a little while ago, and we were trying to do all sorts of stuff. I mean, just mimicking the flat space derivations in AdS. It was not working. I mean, many things we tried, brute force, this, that, this is not working. And the main block was the fact that in AdS, momentum space is not a very good thing. Okay, so in flat space, usually you Fourier transform, and then you can write down Feynman rules, and then these. In many cases, you could sum up all the Feynman diagrams, and therefore produce not trivial results. But e to the power IPX is not a good function in AdS. Okay, this is not a harmonic function in AdS. So, and that was the main block. That's what we realized. Okay, that we cannot make a lot of progress. Just so therefore, what we set forth doing, at least in this paper, is to set up the stage where we can use harmonic functions in AdS to deal with Chern-Simons theories. Okay. Now, the point was that, of course, the harmonic functions in AdS had been studied before, though not, long before. In the recent past, they have been studied, and there is a formalism which was developed essentially by Richkop, Penedonez, and collaborators, who tried to understand. What should be the they discovered a language, in which one can write down these AdS correlators simply. In fact, for an arbitrary, if you have operators with arbitrary boundary conformal dimension and spin, then what is the way to deal with this objects, and what are their propagators? So these could be generally written down based on symmetries. Yes.
Why harmonic function?
Huh?
Why harmonic function?
Because this that's the thing. Right, eigenvectors of Laplacian. That's what I mean. That's the point. Okay, that's it. It benefits just in the same way that like going to Fourier space helps you in flat space, right? So, if you go to Fourier space, then you can write down this 1PIs, sum over diagrams, define them and do things with them. The Feynman diagrams are easy to manipulate in Fourier space, right? So that's the advantage that I am trying to get if I try to, understand what are the harmonic functions and how to express my propagators in terms of harmonic functions. Okay, so this work or this discussion here should be thought of setting the stage for such theories. Let's say you have Chern-Simons theories, theories involving Chern-Simons terms, and what are the propagators in such cases, or what would be the Feynman rules, how to deal with Feynman diagrams or Witten diagrams, so to say, in AdS. So that is the setting up of stage that I'm going to describe here. So let me quickly move on with that motivation to tell you. So essentially, what I'm going to try to do is write down propagators of arbitrary, so I'd like to understand arbitrary spin and arbitrary conformal dimension. So the simplest of such propagators, let me write that because we are going to use it, is an object which is the spin 0, the scalar propagator. So let's say I have some kind of scalar field in the bulk, and this is the simplest object, okay, the spin 0 guy. And similarly, if I have spin 1 fields or gauge fields or spin 1 fields, okay, I will have two indices here in the propagator and two locations, right? This is the kind of object that I'd like to know, how to write down in AdS, okay. And I would like to write this down in terms of AdS harmonic function, harmonic functions in AdS, right? And similarly, I can put in, higher spin operators here as well, and thereby I'll have more indices in this object, okay. So, but one thing I should remember, that this mu index is tied up with the x index in some sense in this way, okay. This is the object I'm computing. So we should remember this, that this mu index is tied up with the x index, and the mu index is tied up with the y index, y location. These are the things that one should keep in mind. Now, yes.
So, now before you get technical, just 2 minutes about the context.
Yes.
So we're looking at matter Chern-Simons theory, where matter transforms in some representation of the Chern-Simons.
Right.
Let's say fundamental, for instance.
Right.
And you want to define a boundary structure that encodes this bulk. Is that,
Right.
Is that
Right.
the motivation?
That's the motivation. Right.
Okay. So I had one immediate question about that, which you've probably thought about, which is that, as you know, in Chern-Simons theory with matter, particles acquire an anomalous spin.
Correct. Right.
So presumably that means that the boundary insertions have a spin which is not some half 1, 2.
Yeah. Yeah.
Now I thought that whenever you have whenever you have conformal field theories and you've got spins such that the spins are not integer multiples of half or 1 or whatever, then such a theory cannot obey modular invariance.
Acha, okay, a modular invariance, right.
Let me just finish the question. So what I wanted, there are two possibilities. One is that you're going to try to explain the strange properties of matter Chern-Simons theories from the known structure of conformal field theory on the boundary.
Or discover new structures.
Or the second possibility is that you're saying that this is a deformation of the structure.
Deformation structure of the conformal field.
Which way do you feel it's going to be?
I think it is going to give us something new. That's my feeling at the moment, but I haven't really gotten up to that point, so.
Yeah, just to have a sense though.
Yeah, so I feel it's going to, so I think it's going to give us certain things that are unusual, and which I think, it was not, while we do 2D CFTs or 2D structure, that is the idea, that, that's why I want to flesh it out. If it maps to something which we know, then, well, it's interesting. Then, even then, questions such as, let's say you have this duality, right? So now you can ask, what is the corresponding thing for this duality from the boundary point of view, in terms of the boundary? Let's say it just maps to some simple, conformal stuff. But then you will realize that either it's the standard 2D bosonization answer, or it's something new. Both are interesting. Both the answers are interesting in my opinion. So, I'm basically after that. But modular invariance, I don't know. What this new structure is going to, come up, that I don't know. And so it's, I think, a little bit premature for me to attempt trying to answer that point. Okay, I really don't know enough about what the structure will emerge at the boundary, because we haven't gotten to putting in matter yet in this game. So yeah.
Just one last context question.
Yeah.
In string theory, we have examples of like AdS3 times
Good.
S3.
Yes. Yes.
In those cases, do we expect any deformation of the structure of CFT?
Yeah, that's a very, very interesting question, because right. So much of what will happen can be also seen as some kind of a subsector. You're saying some kind of a subsector of some known AdS CFT, like yes, you have some Chern-Simons coupling and yeah. So I mean, if it is, if it is something that is there, maybe it does not explode to the extent that that it is visible. Maybe it's there, lying there in some in some boundary theory, in some boundary 2D theory. We haven't really explored that point well enough to know that there are these new structures. Okay, but yeah, as I said,
Or there's some anomaly business.
Yeah, there is definitely an anomaly which is associated with the Chern-Simons terms. That is definitely there.
So which means that anomaly may be that with some kinds of Chern-Simons, it translates into saying that there are that the usual rules of CFT have
an anomaly.
With some anomaly,
Yeah.
but maybe the ones that appear in string theory, the anomaly cancels or something like that.
No, that could be possible. Yeah, that could be possible. Yeah, that could be possible. I mean, there's something nice about the ones that have a proper supergravity embedding. Yeah, I mean. Yeah, the reason I am telling you this is, I don't know, I mean, like, okay. I mean, yeah. Yeah, it seems, okay, firstly, I mean, if you, I'll just make a very speculative comment, which really I didn't want to make, but, so essentially you see in this bulk theory, there are these anionic excitations, right? They should have some kind of a boundary, manifestation, okay? I mean, which should be visible in some way, okay? But in 2D, you don't really have objects, you don't really have the usual anions, right? 2D meaning, 1 plus 1D, so, things won't be going around each other, right? So, it's not going to be the usual anions in 2D. So there has to be some way of understanding what will happen to such anionic excitations at the boundary. And I don't think even in the, those anionic excitations are perhaps there even in theories with the proper supergravity embedding, okay? But they haven't been, like, I think well studied so far. Okay, what is the corresponding thing from the boundary point of view? It's not very clear to me. I at least haven't seen any, detailed understanding of that. Okay, so this is the thing we want to explore. Okay, all right. So yeah.
In your studying is just Chern-Simons in the bulk in AdS3, or is it coupled to gravity?
It's not coupled to gravity. Very importantly, for whatever I'm going to tell you, it's not coupled to gravity. So the CFT data that I'll have will not have a stress tensor, but it will be a valid CFT data. Okay. Now, once I have a good understanding of what's there on the boundary, there are two, one thing is I can try to turn on the, interactions with gravity and try to see, what happens. Although Chern-Simons is topological, but if it couples to matter, which is, which talks to gravity, there will be non-trivial stuff that is happening in those kind of theories. But and the other thing is that there could be certain things which are very universal. For instance, what happens for pure Chern-Simons theory, that there is it's topological. So understandably, what happens in the boundary is kind of universal. You put it in any manifold of the boundary, that happens. That kind of feature may also be there in in certain aspects. That certain thing that you have to, of course, you will have to do something at the boundary, right? If you take Chern-Simons matter theories and put it on any manifold with the boundary, you have to do something at the boundary. And the question is what? Is there anything universal that I can say about it? But here AdS, why AdS? AdS is because, the rules are very clear, and, I know how to find, let's say, the boundary correlation functions, etc. Slightly more under control. That's why AdS. Okay, that's
what role would not coupling to gravity play? What would change if it was coupled to gravity?
I'll have a stress tensor, essentially.
You'll have a stress tensor, but technically from what you're doing, would anything change?
Technically from what I'm doing.
There would be one more particle.
There'll be one more particle. There'll essentially be a spin-2 particle in the game, and I have to deal with the interaction of the spin-2 particle there.
But it doesn't very qualitatively very different.
But it's very so basically I'll do some quantum, so I'll essentially take this and, compute loops at some point, if I evaluate Witten diagrams, that's the hope. And if I want to also put in quantum, the graviton in the loop, I don't know, we had to think about how the parameters go to make it consistent, and that's the point, right? So yeah, so for very clear thinking, I'm just thinking about some field theory in AdS where I'm going to just take Witten diagrams and try to sum them up, or do the perturbation theory up to leading order or first first couple of terms and see what the boundary data is. And that's
this is Chern-Simons with what group? Like,
yeah. So today I will be telling you about abelian Chern-Simons theory entirely. Whatever I'm going to tell you a little bit about Chern-Simons theory is going to be abelian. So, but the hope is I'll be dealing with large n. Okay, at the end of the day, let's say SU and large n theories, essentially replicating the flat space results and taking them into AdS. That's the idea. Okay, very good. So yeah, I will. This is going to be a little bit technical because all I'm going to tell you is a couple of equations and the mathematics that I'm going to use. So these are essentially some mathematical tools that I'm going to talk about, but I hope you will find it interesting. Let me go ahead, unless okay. So this is these are the objects that I want to write, and so the harmonic functions that I will look for should enjoy properties which are similar to these propagators. Okay, that's how I'm going to design it. Okay, for instance, as you know, in flat space, this kind of object would only depend on the modulus of the difference between x and y. Okay, also I'll be working in Euclidean AdS for the time being, and so that is like a symmetry put into the game, right? So I will, if then I will try to look for functions that has this property, this symmetry property kind of built in. Okay, so in AdS what happens is there is an object, these 2-point functions are functions of a variable, which corresponds to this R variable, if you like. Okay, so I'm writing down the scalar one first. So this is essentially, let me write down the expression. So I'll work in, so let me write down AdS3, metric is Poincaré, simplest that you can have, and that's like, there will be lots of z's floating around, sorry. Okay, so this is the metric, and we want to, for the scalar case, let me say that first, it's easy to understand, and it's also very fundamental in some sense in the whole game. So this object is a function of u. Now what is this u? This u is, has this expression, x minus y for finite distances. So let me write it explicitly, zx minus zy plus x1 minus y1 whole square. Okay, that's the usual distance, x2 minus y2 the whole square divided by zx zy. Okay, that's the expression for u. Okay, this has a geometrical interpretation in the sense, this is a very, it's like an object which is invariant under the full isometry of AdS, and this has the geometrical interpretation of being like, if I take 2 points in AdS, then it's the chordal distance. What do I mean by that? Chordal distance means if I think of AdS as a hyperbolic slice in flat space, in one higher dimensional Minkowski space, then if I take 2 points and calculate the distance between these 2 points, that's the u for u. Okay, I mean it's related. There's a +1. It's related to that distance if you like. Okay, so this is my main parameter,
but
and
not the geodesic distance, right? In AdS.
Not in AdS. That's the point. It's not the geodesic distance in AdS. It's the chordal distance. So you have to think of AdS literally as a hyperbola in Minkowski space. Okay, and then you take 2 points and find the line join. It's the distance of length of the line joining the 2 points. Okay, that's the object.
The analog of the sphere would be cos of theta n hat 1 minus dot
correct.
So cos of
Right.
the angle versus the angle.
Correct. Yeah. So this, I mean that's a very interesting. So much of what I'm going to say, I'm not sure if that has been worked out in S3 also. So, there's a question, even, what the kind of questions that I'm asking here would, I think, is also interesting to work out in just S3, okay, and understand these theories, but that's a different story altogether at the moment. But S3 will not have a boundary, so that's not what I'm after. So, let's take this object now and try to so I want to express this object in various theories. I want to find in various scalar theories. So I want to write down functions in AdS, which is just a function of u. Okay, right? Which solves my, which are eigenfunctions of my Laplacian operator. These are my AdS harmonics. Okay, so scalar spin zero AdS harmonic is an object which is a eigenfunction of my Laplacian, okay, in this way, and this I'm going to parameterize by mu, okay, and xy, it's a function of u, right? These are functions of u, essentially. That's what I'm going to assume. This thing is just u, the dependence in x and y, okay, comes in through u, and this is the equation I can try to solve, okay. Let's try to understand that. When I say this is the Laplacian, it's a Laplacian either with respect to x or with respect to y. Doesn't matter, because here I have this exchange symmetry, right? And this should be built into my function here, and that would be there. Okay, that's true for all the 2-point functions that I'll talk about. Okay, so it doesn't matter. So I'm not writing explicitly x or y. You can take anything. And the procedure, let me just say once that the procedure of finding the, so we can solve this and find the exact form of this omega, okay. And so if I write this equation in AdS, and if I move to these variables, you'll see magically the equation becomes just a, a differential equation in u. Okay, it's a second order differential in u. In fact, it's a second order, associated Legendre equation in u. Okay, up to some, dressing of, factors.
Function at x equals y?
No. This is just the eigenvalue equation. This is not the propagator, but this is the harmonic. This is, I'm talking about AdS harmonics. That's why. Okay, in this sense, it's the AdS harmonic. So, the delta function will depend. So, if I put in the delta function here, I'll make it a particular theory. I'm looking at a particular theory, but that's not what I want. I want to take a theory, and I want to express the g's in terms of these omegas, and then I will have a spectral parameter, which is this mu, which is going to be my momentum. Okay, the analog of
in S3, this will be the analog of the Legendre polynomial, right?
Legendre polynomials. Here it's also
the particular spherical harmonic that preserves SO.
Everything, correct. And here also it's some associated Legendre polynomials. Okay, so up to some dressing. So I'm not going to write down the exact expression for it. It's some. But let me tell you about the procedure of solution. So now you have a second order differential equation, right? It has two solutions essentially, but you pick the one which is regular in U. Okay, you pick the regular solution, and that's how you see this is a differential equation in X. But this boundary condition that it being regular at U puts in this dependence on Y as well. Okay, that whatever I will get, must be regular at U. So by that, I'm throwing away one of the solutions, one out of the two solutions, and there is another solution whose normalization is arbitrary. Okay, and that other solution is associated Legendre. This is the Q. The associated Legendre Q. Okay, not the P function. And then there is a there are some factors of U also. I'm not getting into that detail.
So regular means at U equals 0?
Yes, at U equal to 0, it's regular. Okay, so that's the thing that I'm putting into this equation. Now,
and at the boundary, it's always normalizable?
No, it has both the modes at the boundary. So I'm not looking at the boundary. So I'm just, saying that, at a point in the bulk, this is regular, this object is regular. Okay. So, as of now, I'm not putting in any boundary conditions here. Okay, so this is more like a, if you like this is more like how should I say? Once I take this and write down a propagator, then I have to worry about, where I'm putting in, I'll write the propagator down, then I'll put in the sources, etc., and then worry about its normalization and non-normalizability. So I haven't written the propagator yet. This is not the propagator.
This is in Euclidean AdS.
This is in Euclidean AdS, right? Okay.
Yeah, so there should be no normalizable solution that no normalizable solution.
Right. Right. So, but the normalization, so out of the two solutions I picked up one, the normalization is fixed by this following criterion. This is the identity which I had a very difficult time proving. Okay. So again, I'll be slightly sloppy about the factors and the minus signs. In the paper we have checked everything in Mathematica, so all the factors are correct in the paper, but here, I'll not be very careful with the factors. But essentially this expression, okay, which is, if you like, a completeness relation, fixes the normalization of this object. Okay, that's how we are fixing the normalization. Apart from this, there's also a orthogonality which exists, so if I integrate over AdS and take two of these objects, x and y, let's put a new, inside the argument. One has a new argument. This new is the new for the, which eigenvalue, and or the which eigenfunction, and then let's y and w, let's put another new bar. This object is equal to half. There are two delta functions essentially, new plus new bar plus new minus new bar, and then it's also proportional to omega. Of course, you can see y is integrated. Sorry, here I mean the y variable is integrated over. So this is a function of x and omega and any new essentially. I mean new essentially. Okay, so this is a orthogonality relation in some sense. Okay, and I mean, you can argue. So one thing is like, the omega appears on this side also. Okay, so if I take these two omegas, multiply them, I get back a omega, and this is the structure, right? So
Flat space omega would have been like exponential ik dot x, and
it will be ip dot x minus y.
I'm just trying to interpret the two equations that you wrote now
Huh.
as like the integral over momenta of exponential ik.
Is the delta function? Yes. And this two, this is just the orthogonality generalization of that. Yeah.
And there would also be a spherical harmonic, where the sum over nu would be like sum over L, right?
Right. If you do a spherical harmonic, right.
So I suppose what is not obvious here is the measure for d nu, right? Could have been more complicated.
Could have been more complicated, but it's simple. Well, if there is any measure, I'm going to absorb it in this normalization. If there is a measure actually, there is a new measure. So whatever this function is, you see, this normalization is arbitrary up to nu. I can put in any nu here. Okay. So I'm going to do that. Okay. Whatever measure is there, I'll put it in here. Okay, that's the point. So keep this thing simple. Okay. Good. So all set up. So this is the structure of the spin 0, right? This is the structure of the spin 0. Now let me tell you what happens to spin 1 very quickly, and that is the point where we come up with our new thing. So
sorry, one more question, which is probably stupid, but when we, so you've got this, it's probably stupid, but when we do physics on such a theory, in Lorentzian space we have a different kind of inner product. The integral is over two coordinates, and there's a Klein coordinate now.
yeah, okay.
Is there any connection between these two different? It's probably a stupid question.
Right. I
suppose you've not put equation of motion in here.
No, there is no equation of motion yet.
So my Lorentzian norm requires an equation of motion.
Right.
And so this is somehow in some off-shell space.
This is some off-shell identity. Yeah.
Sounds good.
Yeah, this is some off-shell identity, which is also consistent with this expression. As you can see, if I take nu and integrate, okay, so let's say I integrate over nu, I will get this delta, so I'll get a omega here, and this delta will click and give me the same omega. Yes.
All of this should be studied in like harmonic forms in hypothesis, right? In math literature, all those.
I'm sure, but I'm not very sure about the modification that I'm going to tell you. It's there in the maths literature. Usually, these subtleties about parity, even and odd, are, sometimes, ignored, or I don't know. Mathematicians, already know all these things. I think, that's fine.
Sunrise is function to forms right now.
Forms. Yeah. Right. So with that question, let me tell you, I could actually take here higher spin objects, okay, which are forms, or which are also, they can be spin j, like symmetric traceless objects, that is also possible. Okay, so I'm not restricting to forms, so okay, for spin 1 you can call them 1 forms, but in general the thing is going to be applicable for J symmetrized indices, that is possible. Okay, so good. And so let's immediately move on to spin 1. Okay, let me write the spin 1 here. I will summarize on that side. So the spin 1 has two things. So of course I want a solution of this equation. It has two indices, as you can imagine, because my propagator will have two indices. So my spin 1 harmonic, I will put in two indices here. Yes.
The Klein-Gordon norm I was talking about, maybe the restriction of this norm to a particular representation. Could that be? Because then you put delta function of del square minus something is equal to 0.
Right.
Okay, and then you solve for del 0 in terms of the rest.
Right.
And then you get the 1 over omega.
Right.
It's omega squared there, roughly.
Right.
So maybe this thing restricted to a particular this is an overall representation.
Overall representations, right.
But if I restrict your norm to a particular representation, I feel we'll get Klein-Gordon norm.
Yeah. So I think another way of saying it is like, so if I, you'll see that, let's say I want to now find a theory where, I have a scalar field which solves the Klein-Gordon equation, and, I want to express that object in terms of these variables. Then I can use this delta function here, this expression for the delta function, okay, to write, let's say, the G in terms of this. Then you will see there is a factor of, coming in the denominator. Yeah. That's what you're referring
that's
to.
What I'm saying.
Yeah.
Particular representation is equation of motion.
Yeah.
And so once you have a particular representation, it makes sense to impose like phase space kind of.
Right.
It would be natural to restrict it.
Yeah, so it will naturally come over, that's my objective. So I want to take a G and express in terms of omega, and if the equation of motion that G satisfies is the Klein-Gordon equation, then you will have terms in the denominator here, which follows from this expression, essentially. Right, yes?
So for each loop there is only one harmonic function?
Yes, the nu labels the harmonic functions. And nu runs from -∞ to +∞, continuous. Yes. This is a thing. So this is the thing about AdS. I know, you are looking for like 3 numbers if you like. This is the thing, right? But there's one parameter. This happens because I'm restricting to a particular class of harmonics. Okay, I'm not saying that I'm writing down the most general harmonics. Okay, so presumably these harmonic functions can have generalizations, including more parameters. Okay, where it's not just a function of u. This one? Yes. This one will have both plus and minus. Yeah, this is just nu as a function of, So you can write any one because there is a delta function here. You can write any, nu. Yes.
The equation of symmetry in
nu,
right?
Yeah, so I should label them with nu as well. That's the point. Okay. Right.
This quite commutes with like derivatives on x and x1 and x2, right?
Yeah. Nu is a parameter, spectral parameter.
Like go to momentum space in that transverse
In
direction.
say that again. That could be important.
Like
Momentum
x1
space.
and x2, you could have just gone to plane waves, right? Like I think that was.
Yeah, I mean, right. So if you say that, there could be additional quantum numbers if you move away from U. Okay, from the structure of U, there could be additional quantum numbers. But as far as as soon as you say make the ansatz that this is a function of U, there's just one equation involving U. So you solve that, essentially. Yeah. So this is basically solving the eigenvalue problem with a specific ansatz, essentially. That's what it is. So so yes. I'm thinking of it in that way. Yeah, that's the idea. It's like conceptually it's like the radial momentum.
So
yes.
This will be the other two momenta.
It's not important. It's not going to be important for the discussions. Okay, so everything will be symmetric. So it will not be important, right? So good. So for the spin 1 case, you see, I will classify them into 2 parts. One is the so-called transverse one. So I want obviously solutions to this problem, the same problem, but here I have one, and for reasons which will be clear very soon, here I have 2. So this is just a parameterization. I could have called it nu tilde. It doesn't matter. It's an eigenvalue. Okay, and transverse means that if I contract it, so this is now going to be important. You see, so this new index contraction should be with respect to, and then it should be a derivative of x. The one that goes with mu, and that object should be 0. That's what I mean by transverse. Okay, so it's divergence free. Okay, so there will be objects like this, and there will be longitudinal objects for which I will have basically this equation, and whose divergence will divergence will not be 0, but will be some specific thing. So this is, I'm going to denote by a different notation. Let's say, let me use a sigma notation. Okay, so this is my longitudinal ones, and it will have the same form of the eigenvalue. Okay, that's going to be my sigmas. Okay, so I want exact expressions for these objects. Okay, and then go on to discussing specific theories. Let me write that down. Okay, so this object, you will, okay, first let me write the structures down, and then I will tell you where. So
the middle equation there was also new.
It's everything is a function of nu. I'm sorry, I should carry this new index. Huh?
Like on the second one?
Yeah, there's a new index. Sorry. Yeah. I'm sorry. Yeah. So this so this omega, the transverse object, okay, that essentially has a part which I'm calling even, let's say, okay, which is like this: del u del x mu del y nu, and some arbitrary function which I'm calling omega of 1 of nu, okay, plus del u del x mu del u del y nu, okay, I have to write this because to distinguish between x and y, and omega 2 u, okay. So where these two are known functions, okay.
This is what we would call a vector spherical harmonic.
Vector spherical harmonic, exactly, on S3, yeah, this is a vector spherical harmonics. Okay, and similarly we can write down like the spin J spherical harmonics. Okay, so this object has, I'm calling it even because there is a generalization of this which I'm going to talk about, and that's our main, one of the main contributions. So this thing was discussed a lot in these papers by Richkov and João Penedones, the spinning AdS paper, okay, spinning correlators. So this is the form, and this is one form, and interestingly, so this is one form, and so there is a odd part. Let me write these objects down, and then I will explain. So there is an odd part, so this is the parity-even solution to that equation, and apart from the parity-even solution, there is a parity-odd solution as well. I will tell you, how to understand them, but I'm just trying to write down the results right now. So there is a epsilon mu alpha beta del u del x alpha del u del, it's significantly complex, beta and del y mu times some function of omega 3 of u, okay. And so these functions are simply expressed as some differential operator involving u on the simple, so 1 by mu square omega, just omega. That's like d1 operator acting on it. It's a complicated operator. That's the expression. So you take whatever function you have obtained here, omega, divide by mu square, and take a specific operator again, which I'm not writing down. Okay, you will get that omega 1. Okay, I'm just talking about the solutions. It so happens you can, the way I'm telling it, you can just check that this is a solution. You put in this ansatz omega 1, omega 2, you get two equations for them. You can solve it the same way that we solved this, and then you will find that it is related to this omega in this particular way. There is an understanding of this, why it comes out like this, and that was beautifully explained in this in this paper of AdS, this so-called embedding space paper, right? Now this is our function, and this function is also quite simple, and in fact this function is a simple u derivative of omega. This can be written in various ways. It can also be cast into this omega 1 and omega 2 because of these relations. It can be cast in terms of that also. So these are essentially hypergeometric functions, simple to write, if you want to write them down simply. And they are related by derivatives to this, associated Legendre equation with some dressing.
Just about labeling.
Yes.
Now, the group, the associated group for such things is some real version of SU2 times SU2, right?
Yes.
Okay, so we can label all representations, and the real version will be such that it's SL2R times SL2.
Right.
So we can label all representations by H and H bar.
Yeah. Okay.
Of the
Yeah.
So this nu there in that language, first for the scalar, is H equals H bar equals nu in your language.
Yeah. Probably you are right. I haven't thought about it. Yeah. For the scalars,
It has to be H equals H bar.
H equal to H bar.
I presume you've chosen the nu so that H is H bar. Like the lowest energy state in this thing, will it be, will the lowest energy state be of energy nu in Lorentzian space?
Lowest energy state in
To go to Lorentzian space, look at normalizable states. Now you've got a discrete spectrum of states.
Right.
Yes?
Right.
In that, so now the spectrum of states starts at some energy and then
Interesting.
increases by integer multiples.
Yeah, and you're saying the lowest energy state is the new state.
New,
Yeah. It could be. I haven't checked it.
Okay,
Yeah,
you
it
assume
could
that's
be.
the case. This
Yeah.
is H equals H bar equals nu.
New.
Now, these guys that you're talking about, what representations are there?
So they are, these guys are, so they have this, if you like, it's in the symmetric tensor representation of, so this is in the SO4 language, if you like, okay, or SO3, 1. So this is the symmetric tensor of that. Okay, this whole object is a symmetric tensor of that. Okay, and so
I think that means H equals H bar. Right? Because it's like in SO4 language, it's two boxes. So that's J1 plus the SO4 highest weights are whatever that and 0.
Right.
And then the J1 and J2 are that minus 0 plus, over 2 and that plus
0.
Over 2.
Yeah.
Right. So this you're saying is H equals H bar?
Yeah. Right.
No, I'm saying something. Because the vector should have had H minus H bar is 1. This is a vector spherical harmonic.
This is a vector spherical harmonic, yeah. This is a vector spherical harmonic and the vector index is just 1, right? So, when I say, there are 2 points involved. So, it's like, it's literally, forget about y. Then it's just a vector.
It's a vector. I'm trying to understand all states as a function of x.
Yes, then it's a vector. Yeah, I said that wrong. Yeah, then it's a vector.
It's a vector.
It's a vector. So basically, let me tell you this. This is going to be important. This, we are in AdS, right? So we have to take covariant derivative, right? So here, the covariant derivative that I'm acting here is the covariant derivative acting on vectors. Okay, so the connection I'm choosing here is that of vectors, not a tensor. Although it appears that way, but here, yeah.
But so it seems to me that you're going to get H and H bar differing by plus or minus 1.
Okay.
And maybe these two representations are those with some linear combinations of those two.
Could be. There are 2 representations. One is even, one is odd.
One is even, one is odd. And I'm saying, so to say, there's a representation with nu and nu plus 1, or nu plus 1 and 1.
I see.
I'm calling H and H bar. And that some linear combination of those is this, presumably, right?
Yeah, could be. Okay, I haven't thought about it that way. Yeah, but
and even sounds like plus. Because it doesn't distinguish chirality.
Yeah.
Whereas odd will probably be minus. So H plus 1, H plus H plus 1.
Right.
And H plus 1, H minus H plus 1.
Right.
And in that language, with luck, nu is. Do you still have a nu here? Yeah, you have a nu.
Nu, yeah.
So with luck, H is nu. So nu plus 1 nu and nu.
Yeah. So nu is always there because it labels my, eigenvalues. It's the spectral parameter. Yeah, but this is the structure. Yeah.
Overall
So
means the symmetry and symmetry, right?
Uh-huh.
In
Sorry, say that again.
Even what just means like symmetric and anti-symmetric in between, right?
No, this is also, this is one very interesting point, So this is also symmetric. So if you exchange mu and nu and x and y, it's going to be symmetric, although it doesn't look like one, right? And very importantly, there's a, you have to convert this into a tensor. So this a tensor density, you have to multiply by root g factor to convert into a tensor. So, this epsilon as written has the root g as a function of x. But if you now interchange x and y, that changes and then it like becomes, symmetric. So the symmetry property of this is very non-trivial to check, but it turns out that it checks out. Yeah.
Does something special happen at either nu equals 0 or nu equals 1 to this?
Oh, the functional forms.
Reduction. I'm thinking one of L0 or L0 bar is 0. Then you get a new null state. So is there a shortening in this either nu equals 0 or nu equals 1?
So is H
Nu equal to 0, okay.
What?
is H or H1 literally nu or is it?
This is what I'm trying to
Or
understand.
is it half plus nu, half minus?
I'm not sure.
Because in scalar field case, I would think it is like half plus I nu, half minus I nu. Those are the two modes. So, mode function for the scalar. That's what I was-
Maybe it's half plus nu and half plus I. H and H bar should be here. Or not. I was thinking that we're dealing with actually real things.
Yeah.
But maybe it's half plus nu and half minus. Maybe half plus minus 0. But okay, we'll see. I mean, something special. What I'm saying is that when you get a chiral mode, something special should happen. And we should be able to say that. At what value of nu that happens. That will give us the transition.
I see. Yeah, looking at the explicit forms, maybe one can say. Yeah. Yeah, I'll have to check that. Yeah.
So nu square plus 1 for the scalar and nu square plus 2, that should also be somehow related to the representation.
It's related to the j, the value of the spin.
It's the,
Yeah, it's related to the j. Yeah. So that's that, and the longitudinal part is also similar, but the longitudinal mode. So this is the sigma. It's doesn't have the sign. Firstly, you can exactly write it down. It's also the same structure is there. Okay, essentially. Okay. But this has different functions here. So let me call it some mu 1 tilde plus these are functions of u, and they are simple functions of u. But there is an interesting statement about the divergence as an identity. If you take this object, let's say alpha, this thing, this is exactly equal to nu plus 2. This is a very interesting identity, which is very useful while dealing with the theories that we are going to deal with. So this is a yeah.
Just one second. Just for Omkar's question. It's interesting because Euclidean versus Lorentzian kind of thing. So is do real nu's correspond to real masses?
Real nu's correspond to real masses. So if you take a massive real nu corresponds to real nu's. I mean, you're asking. So this is a very theory specific question, like in Chern-Simons theories, or like representation.
Just take the scalars.
So
if I want to get a real mass in Lorentzian space, or in Euclidean space. Does that correspond to real value of nu?
That should be visible from the.
It looks
so
like it's plus m square.
yeah, it's plus m
But
square.
it's plus m square or minus m square is the sort of question.
Huh.
Because
So
the nu square plus 1 was I.
So right. So let me try to answer it here. So if you
plus m square.
so if you so this
Then it's real.
so plus so for a Euclidean case you will have a plus, so let's see. So this is,
Wouldn't it be minus del square plus m square? Because everything's positive in Euclidean action. Del phi, the whole thing squared, plus m
yeah.
squared.
So
And now integrate by parts. Minus del square plus m squared.
minus del square plus m square, yeah, that's the thing. Yeah. So minus del square plus m squared, if you take and you, let's say, this is the equation that you want, right?
Yeah.
Omega equal to,
You
or
see
g,
that's the
let's say,
opposite sign.
this g equal to minus delta, you know.
Yeah, let's set to 0 for a moment, because that's what you have here.
I mean,
Let's say y
well,
is just some parameter. So here you have del square plus m square. Del square plus m square if m was 1 plus mu square.
right,
So it feels like your mu has an I.
Right.
Minus del square minus m square, right? Because minus del square is like energy square minus momentum square.
Let's be in Euclidean space.
Yeah.
Action is positive definition.
Yeah.
Definite. So del phi the whole thing squared plus m squared.
right.
Del phi whole thing squared plus m squared phi squared. And then you just get this, right? So it feels like your positive news, your real news are not real masses then.
At least not in this convention. Yeah.
I mean, not after a point at least.
Yeah.
This is because of Euclidean.
Euclidean. Yeah, so I think you're right because it's the Euclidean representations that have this simple orthonormality, this principal series kind of thing, that have the simple orthonormality that he's written down here, not Lorentzian representations. So I think you're right. Yeah.
I see.
So then chiral modes will not be.
Then it's not.
possible.
Then I'm not. Unless, yeah. Then I'm not sure what I'm saying. It's not. We're not labeling it in the same way as.
Yeah, this new level, how it maps to the representation, yeah, I don't know. And yeah, to see. Okay. All right.
Yeah, but
Yeah.
we should still have a labeling, just maybe with some eyes in the news.
No, like if it is half plus I nu, half minus I nu, for any real nu, the difference is you cannot make one of the either H or H bar 0.
Cannot make either H. Oh, you're right. You're right. You're right. You're right.
Oh, okay.
But what's confusing me is that we're getting a massless guy. Massless, let's say m equals 0. That you can set here. No,
Yeah.
you can't.
Nu is I.
A nu is I. Okay, but let's say we set nu equals I. That should be the same as h
Nu equal
h phi.
yeah. Nu equal to I is the same as, right.
I'm getting confused. Yeah. Okay, but
Yeah, so this will come in the denominator.
presumably eventually you're interested in real masses.
Yeah.
So if you're going to work with something that is not a real mass, you'll analytically continue later.
So actually, I will, so essentially at the end of the day, I will try to, let's say, I want to solve for the G, right? So I will have a expression which is, for instance, I want to solve this delta function equation, right? So for this delta function, if I substitute, then as you can see, I will have a nu square plus m square plus 1, right, in the denominator. So this object G will be some integral of omega nu square plus m square plus 1, right?
Right.
Okay. And then I will basically try to do this integral given I have a set of poles. That's the idea.
Yeah.
Okay.
Yeah.
So
So once
that's-
again, from the denominator, we see that m square is equal to minus of nu square plus 1.
Right.
That's where you have the pole.
Right. Right. Yeah. It's the location of the pole. Yeah.
Okay,
So
got
this is
it.
what.
Got it.
This is what
So it's
we
like
want.
working in the principal series and then analytically continuing to where you want to be. Since in the end, where you want to be is the Lorentzian place. Finally, we'll still be able to ask the question: what is H and H square?
Right. Okay.
After doing whatever, it's got some mathematical tricks. But in the end, we will be taking the poles, right?
Yeah. In the end, we will be taking the poles. Right. The poles will matter.
At real values
Yeah.
of mass.
Right.
So that will be actual representations.
Right. Right. Right.
Are not going to satisfy this optimal.
No. So this is a trick.
I mean, this integral is over real nu, right?
This integrals over it.
The integral is real name. Yeah.
It's some trick, and in the end, we analytically continue. I think that's
Right. Okay. All right. So right. So this is like a summary of like the structures. Now, so So to tell you, how we got this, so the first thing is that, these structures were there in this previous papers, and at least, structurally, they follow from this so-called embedding formalism. So if you ask, this symmetry group, acts linearly in one higher dimension. So you go to 4 dimension and you try to write, so these objects can be thought of as like quote unquote tensors in 4 dimensions, and those tensors can be encoded in a polynomial. So you write down the most general Lorentz invariant polynomial given some, given the objects that you have here, and then from there you can reduce. I will try to summarize this at the end if I have time, but here these results, just follow from that formalism, this one and this one if you like, and the structures.
What we always do for side lab.
What we always do for, put it into a one higher dimensional space, and then we want to look at it. Yeah, that's that formalism. Okay. So now, but this one, this one can also be seen in that formalism. So we kind of generalize that formalism to obtain this as well. So again, I'm not right away going into that. I will summarize at the end if there is time. But let me tell you something more interesting. Which helps us a lot with our calculations here.
Is that using an epsilon tensor?
Epsilon tensor, yeah, in 4-dimensional epsilon tensor. Okay, and so let me tell you something which is slightly, that is there. That is the generalization. That is one way of thinking about how it comes. There is another way of thinking about how it comes, and it kind of matches. So let me tell you the other way, which I think indicates a very nice, interesting mathematical structure here. So what happens is, if we are interested in this these kind of functions in 3 dimensions, so in 3 dimensions we can define this so-called Hodge Laplacian or the Laplace-Beltrami operator. Okay, which so here I'm going to describe something which I call the Chern-Simons operator. Okay, which plays a very central role in all our calculations, at least simplifies a lot. Okay, so what we have here is, so let's take this Laplace-Beltrami operator, which is essentially d delta, so d star plus star d star d, and this, looking at this, let us define a Chern-Simons operator, let's call it a curly d, as star d. Okay, and so when this operator acts on forms, let's say it acts on 1 forms, let's look at the action of this operator on 1 forms, then and if we have the 1 form which is divergence free, then this term doesn't act, right? So on divergence free 1 forms, okay, this object, okay, let me denote it by omega only, is equal to star d whole square on that 1 form schematically. And if you want to put in, you can also write this Laplacian in terms of the you can write this Laplacian in terms of ordinary Laplacian involving the the Christoffel connection. And if you do that, so let me put in an index here, it's easier to write. So this is equal to minus this Laplacian plus certain things. Okay, so this is exact, so this is just r mu nu omega nu. So on a 1 form this is like exact, so this has some curvature terms, okay, usually. Now this curvature term for a maximally symmetric space like AdS3 is proportional to the metric, right? And it's proportional to metric if you set the AdS radius to 1, which I did. This turns out to be exactly minus Laplacian square plus 2 times this omega nu. Sorry, nu. So on a 1 form, you see the square of this operator is the Laplacian shifted by 2 on a 1 form. Okay, if it is divergence-less. Okay, so this object, therefore, which I can write in components. So if this on such forms in our notation now, where we have two indices, mind you. So there is a new index which is the main index, okay, with respect to which this operator is acting. So this is actually, I don't think I will have space here. So let me still try to fit it in. So there is a epsilon mu alpha beta. Right. There's a del alpha and omega beta nu. Okay, the new index goes free, it's the other part. Okay, so this is in terms of expression, and so in our language, this result, this particular result, reduces to the fact that if I have a d square acting on such omega mu nu, then this will simply be my Laplacian minus of Laplacian plus 2 on Laplacian plus 2 on this omega mu nu, right? Okay, so this is a very interesting structure that we already have here. Now, right. So before I finish this discussion, let me mention something which I found interesting. It's that there is a generalization of this. So you can now ask that if I generalize this to, let's say, J spin objects, okay, so I can define a similar operator D on an object which has J spins, let's say mu1 up to mu j, which is of this form, let's say sum over some mu k. There is symmetrization involved in the Chern-Simons, mu k alpha beta, okay, del alpha and phi mu 1, somewhere I put in the beta here, mu j, okay. So this is the j, this I'm assuming symmetric traceless object, okay, on which I can define such an operator. And so what we observed was that this del square is also very simply related to the Laplacian. So this object mu1 up to mu j is this is something which we just, while calculating, we observed this Laplacian minus Laplacian square plus j into j plus 1. So that reduces to 2, as you can see in for j times phi mu1 up to mu j. So this object, but it so turns out that this again for maximally symmetric spaces is a generalization of the Laplace-Beltrami operator. This has a name. It's called, I think, Lich-Nerowitz operator or something like that. Okay, I didn't know about this before. I googled up and then Gemini gave me the name. Okay, I never heard about this. But yeah, so this also apparently is some nice quantity which comes out for a general symmetric, there is a generalization of this to general, symmetric traceless objects. So that's that. But with the help of this has another, so this is the nice structure about this operator, but this has some very good features. It squares to the Laplacian. Okay, this is an operator that squares to the Laplacian, and not only that, it has some very nice action on this on these forms. How am I doing? My God. Okay. So how does it act on these forms? So it acts in the following way, that so if I take this del and I consider this even object, okay, if I consider the even object, as you can guess, this, because this del involves the Chern-Simons term, the even object gets converted into the odd object, okay, which is this the other thing that I wrote down. I'm not writing down the arguments, you understand, okay. Similarly, if I act with the D on the odd object, then I get back the even object, even harmonic forms for all nu, but here I have a nu square, okay. So there is a relation like this with the operator, okay. And this is one way to figure out what this answer would be. You just take it and act on this, you will get this. Take the Chern-Simons operator, act on this, you will get this, okay. And also let me write down the D on this sigma, the transverse one, okay, that just vanishes, it just kills it, okay. So now with this structure, you can write down a new harmonic function, Okay, it's harmonic because it's going to be a linear combination of even and odd harmonics, okay, which is of this form, even plus 1 over nu odd, this thing, which clearly is a eigenfunction of the Laplacian, clearly, but it is also an eigenfunction of this Chern-Simons operator. You see where I'm going with this? Now, wherever the Chern-Simons operator appears in the equation of motion, I have the functions to, write that particular propagator with, right? So that is the idea. So here we take this and we write it as, let's see. So it's just, I think, nu times. So it's very clear how it happens, because if you act it with this operator, then E becomes O directly, but O becomes E with a nu square, and then you pull the nu out to get back the same function, you get this, right? So nu is the eigenvalue of this D operator, whereas on this the Laplacian acts as with the eigenvalue minus of nu square plus 2 again. Okay, that's the structure. So this structure helps us a lot. So everything that was said in these papers involving the even harmonics, I can just take my D operator and convert into my odd harmonic result. Okay, that makes life very simple. Okay, because of this action, right? So this I felt was very nice about, it helped us with the calculations a lot. Also, this gives you an opportunity to very simply deal with a theory which has both a Maxwell term as well as a Chern-Simons term. Yes?
Is it like that a vector in 3 dimensions will have 3 modes and you've somehow decomposed it into one longitudinal, 2 transverse, which one is even, one is odd?
That's an interesting way to say it. Yeah. Yeah. Yeah.
I feel along these lines, if you have h plus 1 and h, plus h plus 1, is converting it into h plus 1 plus h minus h plus 1, which is very simple.
Yeah. So of course the longitudinal is the 0, if you like, and then you can,
The h plus 1, h is one polarization.
Right.
And h plus 1 is the other polarization. And here we're doing one linear combination.
Right. Yeah. Yeah, and one, yeah. Right.
From the point of view, SO4 representation there, it's like self-dual and anti-self-dual.
Right.
Self-dual and anti-self-dual, right.
I'm thinking, but I'm not
sure. Yeah, I have to check that language a little bit. Yeah, that's a very good way to think about it. Yeah, I haven't really, at least at the harmonic function level, I was not, thinking about the representation. Yeah, good. So, okay, so this is the basic setup. Now with this, we can go ahead and, deal with theories. Also, so I'm sure I'm not doing very well on time. So maybe I will not get into too much details about, let me briefly summarize, what we can do with this, give you some example, how we can, because there are certain things, there are some subtleties out there which I think we also got confused with at some point, but but the bottom line I want to say is all of this can be derived from this embedding formalism. Okay, so you go to this, one higher dimension, write polynomials down, you'll see that there is a generalization possible using the 4-dimensional epsilon, and with that generalization you can derive all of this. Okay, all of this is derivable from there, all the structures, everything follows. Okay, we've done that.
And is the guy that is odd, something minus epsilon times something?
I didn't understand that.
So, the guy that is even, if it's self-dual plus anti-self-dual, I would have expected that to be object plus epsilon times object. It's too vague.
Yeah, sorry. Yeah, okay. Right. So let's get on to this thing that, let's get down with theories that we want to solve. So,
the thing which you have written here,
yeah.
is it in the embedding space or it's on the manifold itself?
It's in the manifold instance. So I didn't get in the embedding space, formalism at all. Okay, I'm just giving you the results in AdS3 language directly. Okay. So let me, So again, just tell me where to stop. I will try to summarize and stop. So if I,
6 o'clock I'll have to leave.
yeah. So very quickly, let me tell you one thing, which again, so you can first ask that, okay, let's say I have the pure Chern-Simons theory, and how do I deal with that? Okay, just pure abelian Chern-Simons theory in AdS. Okay, that's a very simple thing, and one should be able to work that out. Now that itself was little confused us a little bit, and then there was a paper by Ashok which helped us. So
So in that case, what value of nu is the pole at?
Yeah, I'll just write it down. So, okay, so in terms of these, so now I have combined, you see, when I'm writing down the eigenfunction of the Laplacian operator, I have combined these even and odd objects, okay. So, I'll be writing down now, I'll be dealing with that object, that is my, this thing, right. So, before I do that, so as I said, I can write down all sorts of identities with this object. So one identity is superly useful is this delta function, the kind of completeness identity. So with the even functions, again picking up from these previous papers, I have an identity which is d nu omega even plus integral d nu there's a part which is sigma by I think mu square plus 1 mu square plus 1. The signs are again, I will not be able to track properly, but this is equal to the delta function, okay, with a g mu nu, because all these things have a mu nu index, okay, and probably there is a minus sign. Is there a minus sign? Right. No, there's no minus sign. Okay. So this is identity which is you can verify, using the explicit form of the functions. Now, along with this, you see, we also have this odd object, which out here appears with a 1 over nu, whatever that odd object was. You remember we obtained this odd object by the action of the d on this even, right? That's sets the normalization also. So this odd object is with that normalization divided by nu, and then this nu cancels one of the nu's that appears here. Okay, so there is this function doesn't really have any pole. As written, it doesn't have any pole, and if you integrate this, this exactly 0, just vanishes. Because it vanishes and it doesn't have the pole actually, although despite appearance it doesn't have it because it cancels, then you can just take this and add it in here. If you take this and add it in here, this becomes a identity with my eigenfunctions. Okay, so that's the expression that's going to be very useful for us, because we are now in a theory which is the Chern-Simons theory. So I have a Chern-Simons operator, let's say mu alpha, okay, plus there is a gauge fixing term which is let's say xi is the gauge fixing parameter, the usual Fadi-Popov-Abelian gauge fixing I'm doing. So there is a right. So let's see how the indices went. Acha. Alpha nu, okay, and this is equal to minus g mu nu delta of xy. So you can now see why, how this helps us, because I will now say that my g mu nu is expressed in terms of these objects, right, such that when I act with this operator, I get back this delta using this identity. That's the idea. That's the usual thing that we do. We convert it into a algebraic equation and then solve it, right? So if I do that, then this turns out to be this mu nu. There is a simple nu pole here, okay, and so this is my. I'm writing down the expression for g mu nu, okay, the solution to this equation, which is d nu. There is a simple pole, and then but there is a longitudinal part. Okay, but the longitudinal part, fortunately, is proportional to xi. So this is equal to nu plus, this is equal to nu, right, nu plus 1, the whole thing square. Okay. Right. So this is the answer.
That's pure gauge somehow?
That's pure gauge because it's proportional to xi. Okay. And
this tells us that Chern-Simons is at nu equals 0, right?
At nu equal to 0. Yeah.
Right.
Yeah. Yeah. Right.
So this is probably the chiral.
This is the chiral guy. Yeah. The thing is that you see, right. So yeah, I mean you can work with a gauge where xi equal to 0. You know, that's very standard. So this is the term to look at. So you can now look at this term and you can find what are the what is the answer here. And so if you see the answer, then so you can decode now. Okay, so you do this integral. Okay, this integral is very doable. You do this integral and then you try to, that will give you the bulk-to-bulk propagator. Okay, if you do this integral, it will give you the bulk-to-bulk propagator. Again, in this form, the bulk-to-bulk propagator we haven't seen written in the literature, anywhere. Okay, so this is a explicit form of the bulk-to-bulk propagator, and okay, so right, it's basically this object. Okay, g mu nu is this xy. Okay, is this simple thing. This involving the epsilon mu alpha beta, del alpha del u del x alpha del u del x beta del y mu. Okay, this is this structure, and then this is multiplied by a very simple function of u. It's so simple that I can even write it down. It's u plus 1 divided by u into u plus 2 to the power 3 by 2, or something like this. Okay, it's a very simple function, not even hypergeometric. So this is the answer up to some normalization, some coefficients, which fixes, the normalization is fixed by this essentially. So you see, it's such a simple answer, and then you can take, let me tell you the story now. So you can take this and find the bulk to boundary propagator, and also boundary to boundary propagator. You just take one of these points x and y and put one of them to the boundary. That will give you the bulk to boundary propagator, and take the other one and then pull it up. So that will give you a boundary to boundary propagator. So that in full generality we can find the answer given this given this answer from this answer. Okay. So now the confusion that we had was that that should somehow reproduce the current in the boundary. Okay, so whatever boundary to boundary propagator if we find, this should just reproduce the currents, right? Now if you look at this and convert it into, let's say, the ZZ bar indices in the boundary propagator, we find that both the, if you like, the JZ and the JZ bar currents both are there, both the answers are there inside this. Okay, so if you find the bulk to boundary propagator, so both the answers are there here. So if I just naively take these points to infinity, then I get both the answers. Okay.
You don't get a chiral current.
I don't get a chiral current. Okay, I get both, the holomorphic and the anti-holomorphic, both of them comes, right? So the resolution, I think, we understood from one of the papers that Ashok wrote, in similar case, the resolution is that, if you have to, this is the bulk equation. So the bulk Lagrangian is just a Chern-Simons action, right, here. But that is not enough to give you a chiral current on the boundary. You have to add a mass term. Okay. And now the picture is slightly more clear to us. There's another check that we have been able to do. So if we have this bulk action, which is, let's say, some Chern-Simons term, epsilon mu nu alpha del mu a alpha. Okay, this you have in the bulk d3x. Then on the boundary of AdS, you have to add in a term which is, if you like, so d2x. You have to add a term which is az bar at the boundary. Okay. With a specific coefficient. Okay, so if this coefficient is typically, because I'm Euclidean, I have a I k by 4 pi, then this coefficient must be ik by 2 pi, something like that, related to that coefficient.
Get the equation of cancel that.
That cancel that, right, exactly. So what this mass term does, if you vary this, then you see one of the, AZ, that gets cancelled out. Okay, so that is not something where you can set boundary conditions on. So you have to take one of the, so when you use this propagator to, find the answer for, let's say, you put in some boundary source at the boundary, that source has to be half of the object, and then write down the on-shell action and then vary, then you get the chiral currents essentially. That's the explanation. But the sign, is very crucial here. The sign of this mass term determines whether you will get a J or a J bar essentially. Okay, this is the main point, that the sign determines whether you will get a J or the mass term or the boundary mass term that will determine this. Now, so this is the explanation for the pure this thing.
So it's interesting. So now you understand that you are dealing with a chiral current.
Yeah, we dealing with the chiral current on the boundary.
I see.
Because of this term, you don't have the freedom to set independent boundary conditions for both holomorphic and anti-holomorphic components. Okay, so you just fix one, and therefore the final answer is a function of one only. So you differentiate that to get the answer, and that answer is holomorphic. Then, okay.
Good.
Okay, so this is one thing, and let me tell you now one more interesting thing which I think figured out after putting out the paper. So if we now restrict this thing, there is a subtlety here which we missed. So if we restrict this thing and put in a mass term here itself in the bulk, right? We can do that. Okay, we don't have a gauge fixing term anymore. This is a different theory which you can try to solve. If we try to solve this theory, because our techniques are now developed, we can just write this down and try to find the answer for. Now there are poles. Okay, now yeah. So let me write that's let me write that thing down. So at least the massive poles.
So now the current is no longer conserved, right, on the boundary.
Right. It's not a current also. That's my statement. It's not a current.
Because
it's an operator.
Conserved, right?
Yeah. It's an operator.
So
yeah.
H plus H bar is no longer 1.
Right.
Okay.
H plus H bar is 1 actually. Here also, the way it happens, so there is a mass deformation. So
the Young's term I would have expected H plus H bar.
H plus H bar, no. H plus H bar is not 1. The delta is 1 plus mod n.
Yeah.
That's the point.
On the other hand, if you take Young's term, you change H and change H bar, but H plus H bar will be 1, right? Because the current is conserved.
No, even there, it's proportional to the, if you just have pure Young's, then it is true what you are saying. But if you have the Chern-Simons term along with the Maxwell term, then there is a coupling which is k. Yeah. So it is proportional to 1 plus k by 2. It's proportional. It's shifted.
Is one of them 1 plus something and the other one minus something?
No, it's so let me tell you this explicitly. This is kind of interesting. So whatever you have here is right. So yeah, let me write down one. So let's say there is an even part. Okay. So in the answer, let's say G. Let me schematically write it in this way. So Gxy. Okay. Let's say there is an even part. So G even, okay, this in general, I'm again writing it very schematically, 1 plus u tilde, which is this is like, one variable I have pulled to the boundary, okay. I'm trying to tell you the whole, slightly, the whole story. So this is the bulk to boundary propagator. So in the bulk to boundary propagator, I will have this as 1 plus mod m in this particular theory, and there's an even part. But the even part comes also with a sign m. This is the sign m which we kind of missed in our, it's kind of subtle how it comes from the integrals using the poles. There's a sign m and there's a g odd also which has a similar 1 plus u tilde 1 plus m. Okay, 1 plus mod m. Okay, so what happens here is depending on the m value, okay, this term shifts sign. Okay. And when this term shifts sign, if you go to this ZZ bar basis, like in the complex basis, what happens is, you for one sign of this, you get the Z, object, and the z bar, vanishes because of cancellations between even and odd, okay? And with the other sign, you get the z bar, okay?
Remains chiral.
It remains chiral.
Is not 1.
But,
But
yeah.
H is not 1.
H is not 1, yes. So here you can say in the H, non-holomorphic, right? Remains chiral but non-holomorphic. That's the answer. So there's a if you like, I'm writing down the J, if you like, I'm using J, but it's not a current, JZ, this happens, this you will get as, let's say, 1 by Z, Z to the power, Z goes as 1 plus mod M, and Z bar to the power mod M, okay? So that, sorry, this is, I think I messed this power, this is 2 plus, sorry, I messed this power up. I think this is 2 plus, yeah, because delta is 1 plus mod M.
Yeah, so
Yeah.
H, at M equals 0, H was 1.
Yeah.
So it would be Z squared.
Right. Yeah, it's 2 plus mod M, and yeah, so this is 2 plus mod M. Sorry, this is 2 plus mod M, and this is mod M. So that delta, the value of delta, that is 1 plus mod M, and J, of course, is the difference. So that's 1 plus mod M, and that's 1. J is 1 because, yeah. So this is the answer, okay? And if you do the Z bar, this flips essentially, okay? So, and very interestingly, this depends on the sign of M again. You see, if you set the sign to 0, and so if you now set M to 0, okay, depending on which side you have approached, you get the holomorphic, current and the anti-holomorphic current, which is conserved. If you set now the M to 0, it depends on which side you are approaching, like the 0 from, okay? So these are the, that's the result, and a very similar thing happens with the if you add Maxwell term here. So let's call the ratio of the couplings kappa, because kappa essentially is the ratio of the two couplings. Let's call that. Then mod M is replaced by kappa here, essentially in this structure.
Wait, so now you add a Maxwell term and no mass.
Maxwell term with no mass, yes, that's what I did.
So
yes.
mod M is replaced by kappa.
Mod M is replaced by kappa, and this sign, shifts here now.
Wait, but this current should be conserved with Maxwell term and no mass, right?
Ah, okay.
Right, so which, so then now there is both a J and a J bar, presumably?
No, it's a structure is very similar. J and J bar cancels because of this, there's a sign flip that happens with respect to, what the sign of kappa is now, because the sign of kappa is variable. So depending on that, the chirality flips, if you like.
See, what's confusing me is the following.
Yeah.
That from gauge invariance of the action, unless there's a subtlety, but I would have expected that current would continue to be conserved.
Yeah, I know what you're saying.
So if current is conserved,
Yeah.
and you have a chiral thing, then it has to be analytic. The M thing sounds very sensible. Because it's like a W boson.
Yeah.
And we know that W bosons in Chern-Simons theory have either one chirality or the other. They have one spin or the other depending on the sign of the mass. So that's what you're seeing there. But with the Youngles, this is surprising me that you're getting chiral but not.
You know what? These structures that we have here, the even and the odd. So it's definitely true that there will be an even structure and the odd structure, right? And these structures are fixed by, whatever they are, just this number varies, okay? Yeah. So these structures are fixed by, if you like, boundary conformal invariance, okay? There's not much game here other than just this, as soon as you say you are dealing with a spin 1 field, these structures are fixed and only these delta can vary, okay, in this game.
But then there's some linear combinations you can take.
You can take some linear combinations in general. Yeah, the linear combination we seem to be getting is just plus minus 1 here. Okay.
And then the final answer is it Jz equals only.
Yeah, that's what it's coming, because you see there is no other, it's the mutual sign that determines this. There's no other structure. Yeah, I understand your objection very well. Yeah, I don't know. Yeah. structurally it's, yeah, right.
It would
Unless we, there's this pole structure which, unless we mess that up again.
No, it sounds okay. I'll tell you what I had expected. What I had expected is that
There's a conserved current.
a conserved current, but not holomorphic. I mean, not chiral. Because now with Yang-Mills you have two polarizations.
No, but you also have the Chern-Simons term, right?
Yang-Mills plus Chern-Simons.
Yes.
But once you've added a Yang-Mills,
Yeah.
now it's a second order equation.
It's a second order equation,
So
correct?
now you should expect two polarizations, right? I mean, if you're just thinking in flat space, you would have both polarizations for the photon.
Yeah, for the photon, both the polarizations are there. That's the thing. Because for the photon, if you just, this is the thing. You see, because the sin m term appears here. So if you take that, sin kappa, if you like. So if you take the kappa tends to zero limit, the odd part goes away, and then you have both the polarizations coming from here.
I meant for the W goes up. No, I should say photon, but
Yeah.
just Chern-Simons gives it a mass, right?
Chern-Simons gives it a mass, right?
So Chern-Simons is a form of a mass,
Yes,
and ordinary masses are also a form of a mass.
correct.
But there's a difference, and the difference is that Chern-Simons doesn't break gauge invariance,
Yeah,
whereas ordinary masses do.
yeah,
So that I thought would mean that H plus H bar has to stay 1 if you add just a Yang-Mills, but H plus H bar is not staying 1 if you add just the Chern-Simons. If you have Yang-Mills plus Chern-Simons, H plus H bar is 1. If you have if you have Chern-Simons and mass, H plus H bar is not 1. The last thing is consistent with what you're saying. And I would have naively expected that if you added a Chern-Simons plus Yang-Mills, you would now get both polarizations. So it's not chiral, and one of them would be H, the other would be H bar, but H plus H bar is 1. Something like that. Very vaguely. I would.
Yeah, you're saying that, in the same theory you will expect both the chiral currents, but they are non-holomorphic. That's what you're saying.
Yeah, I would have exactly expect both Jz and Jz bar.
But let's say if I consider a photon, you see in 2D, how should I say, the degree of freedom is just 1, right? Isn't that true? Because because there is a duality, right, in the current.
You can have 1 degree of freedom.
Right.
But you can also have 2.
Right.
Now,
right.
if you take a second order equation with a massive gauge boson, it will have 2 degrees of freedom.
Right.
Because you will have X polarization, Y polarization, each of which will be 1 degree.
Right.
If you have a first order equation, you link this polarization to that, and there will be 1 degree of freedom. Now, because Maxwell Yang-Mills, Maxwell Chern-Simons is a second order equation. Because of the Chern-Simons, because of Maxwell. It looks to me like each polarization has its own life. In a first order equation, like in Dirac, right? This guy gets linked to this guy, and that makes it a second order equation, so 1 degree of freedom. So you have one degree of freedom in the end, even though you have 2 polarizations. But now you've got second order and these 2 polarizations. So it should be 2 degrees of freedom, I thought. Not that I've ever done a calculation. I would have vaguely expected.
Yeah, but isn't there a load okay, I'm confused now, because the 3D photon has 1 degree of polarization, because of the
massless, using massless.
The massless case.
No, but
yeah.
massive. Let's take massive.
Oh, because of the mass you are saying it will get the other mode.
Yeah.
No, but even with the mass it doesn't, because I think, if you do it the Chern-Simons way, if you did a m mass, then you will get both the polarization. I can even see the calculation in my head. If you took ordinary this thing pure Maxwell plus put in the ordinary mass like mu, you will get both the currents, because it'll have this.
Yes.
But if you put in the Chern-Simons mass, I think you still have 1.
If you put Chern-Simons plus a mass, you will have 1.
No, I'm saying that in the Maxwell equation. Okay, so if you put an ordinary mass, you have 2. That's like Higgsing, right?
Yes.
But if you do it in the topological way, I think you still have 1.
You have 1 degree of freedom?
I think so, and that's what we are seeing. Okay. Yeah. But I will have to, I will have to give you a, better argument for this. I think, yeah. So this I'm just recalling,
But, it's just conflicting with this, that if you've got second order, you should double the number of degrees of freedom. Let's compare Maxwell plus mass Sorry, Chern-Simons plus mass. Okay, as you said, Chern-Simons plus mass has 1 degree of freedom.
Yes.
We all agree on that.
Yes.
Maxwell plus mass has 2 degrees of freedom. We agree on that.
Yes.
Now suppose we do both. We do all of them.
All of them will give us 2.
2 degrees of freedom.
Yes. All of them will give us 2.
Excellent. And now you're saying, now if you set the mass
To 0,
you get back
you
1.
get back 1. That's what I'm saying.
Okay, maybe it's right.
Yeah.
Maybe it's right.
At least that what appears from the calculation. I mean,
Maybe
yeah.
it's right.
Yeah, but I'm also vaguely recalling and seeing it somewhere that even with the topological mass, that's why it's a topological mass. That, it keeps the degrees of count, same. But yeah, I'll have to,
Maybe it's right.
yeah. Yeah. Yeah, okay, I will stop here, but yeah, let me stop here. Yeah. Yeah. Yes, please. Yes.
Since it was Euclidean EDS,
Yes.
one can see it as like a constant R slice in the Minkowskian diamond.
Exactly.
So, and it's like
It's a hyperbola in Minkowski space. Yes. Yes.
on a hyperbola in that.
Yes. Yes.
So like
So everything is, everything that I said is derived from that fact.
so that is the embedding formula.
That is the embedding formalism. Yes.
Now,
Which,
what kind of physics is in 4D, which is like described roughly in this 3D, and you can in this 3D you can also like go to a 2D sphere where you're writing these JJs, which can maybe describe the 4D physics. So, I'm just
yeah. So you see, here what we can infer is not dynamics, but rather than symmetry constraints that can be derived properly. Okay. So for dynamics, you have to actually go to the equation and solve, and then you have to worry about things going out of the surface. Dynamics may not be limited to a surface. Okay. So when you see dynamical equations, or what happens to, let's say, propagation in 4 dimensions, restricting it to a surface may not be even consistent. So what the embedding formalism does, it just puts, if you restrict it suitably, it tells you, what the structures are and what the symmetry constraints are on these kind of correlation functions. That can be very easily, obtained from there. But the dynamics question is hard, and I don't think, yeah.
I just thought it's interesting that if you take that hyperboloid as a constant R slice in the Minkowskian diamond, take R goes to infinity or something, then it is like the boundary of that space, roughly. And then
Oh, that's very interesting. Yeah, yeah. So right. But it's okay, let me see. So if you, so let's say we have a cone here, right? So usually we consider a hyperbola like this, and the boundary is like, it's the boundary of the hyperbola, touches the cone. So it's basically, this surface of the cone that we land up into. Okay. So in this sense, because you have to constrain it, AdS goes to, it's not that, so it goes to a null line at the boundary. So yeah, so that's the thing. Yeah, so the usual flat space boundary has, if you like, if you are on the null line, then it's a sphere. But here, if you go to the boundary, yeah, in Euclidean case, yeah, we essentially in the in the flat limit, yeah, right.
there's
Right.
probably a better or different foliation possible or something which
Yeah, this is a very specific foliation. This is a very specific foliation, right?
it was just a wake up.
No, interesting. Yeah. You want to think of the boundary of AdS as the that S2 of flat space. Huh. Okay.
Jyotirmoy, sorry, I still feel that the Chern-Simons Maxwell, that has to be conserved, right? So H plus H bar has to be 1. How can that
H plus H bar.
be? J has dimension 1. Every conserved current has dimension d minus 1.
Let me check. So H plus.
From gauge where the current is conserved.
From gauge invariance, the current is conserved. Every conserved current in any conformal field theory has dimension d minus 1. In this case, d is 2. So dimension has to be 1, and I presume your dimension is H plus H bar. Right? Oh, it's H by maybe by 2. Maybe that's what is I'm getting wrong. Maybe there's a by 2. Oh, maybe that's what you're saying. Could that be? No, not by 2.
So
It should be H plus H.
H plus H bar, yeah, because H is 1 is a marginal.
Z,
Yeah.
No, but this is, let's see, so H is, so this is 2H, right, and this is 2H bar.
Yeah.
So that's, right, so this is 1 plus M is, wait,
Just seems impossible to me. If there was a minus sign there, that would be great.
did we get this? No, but that will lead to negative dimensions, no?
Let's say there was a minus sign in the Z. 2 minus mod M and Z bar to the power mod M. That would be perfect. Because then H plus H bar would be 1.
Maybe I'm missing a minus sign here, that's possible, I'll have to check. But here, okay, let's see. So 1 plus H bar. But you know, if this is 1, so let's see. So this is very, you know, this is some H bar. H is, from here, H is 1 plus mod M by 2, right? And H bar is mod M by 2, right? So if you take this minus this, that's your 1. And if you add them up, that's your 1 plus mod M, delta.
Yeah.
So that's like delta and J.
Yeah.
Okay.
Now
Right.
I'm saying that if we were just with Maxwell Chern-Simons, since it preserves gauge invariance, the current dual to it should be should be conserved.
So you're saying there's a minus sign here.
I
Is
think
that
there's a minus sign. Yes, exactly.
if the H has a minus sign, minus
Then everything
mod,
works.
is that right? Somehow we have a plus sign here, I think. Let me check.
Okay, but was it clear? Yeah, so somehow the spin being 1, maybe that, at least there's no clear principle that it dictates that spin was 1.
Well, I mean, I'm dealing with, you know, spin 1 fields.
The complete the action should be like ABUG.
D mu J one.
So it has one index.
Yeah, it is 1 index.
Well, let's say we do the same for the Chern-Simons coupled with mass. Now H increased away from 1, H bar remains 0, so spin was not 1.
No, but here spin was 1. Spin was 1.
Wait, in which case?
In the Chern-Simons plus mass.
Chern-Simons plus mass, didn't you say that the Z H index increased beyond 1?
So, yeah, so the H index was 2 plus M and this was mod M.
No,
So this minus this?
I thought with Chern-Simons plus mass you didn't have any Z bar. No, you
No, we had a Z bar. Yeah.
Oh.
Yeah, I was like surprised to find, you know, the only difference in the answer, you know, in terms of this schematic, this sign M essentially goes to this odd part. Other than that, it looks structurally.
The conservation is a clear question, right?
Conservation is a clear question. I'm slightly confused by this, yeah. But, yeah, what can be the relative sign? I mean, you know, this relative thing can either be plus or a minus, right? So, yeah, you know, I mean, as long as this is not going away. So if there is a plus or a minus, you know, depending on that, you know, this Z bar cancels. But I'll check this more carefully actually, you know, I cannot work this out. You know, this integral is, you know, this is the integral which I think, you know, on the first shot we got wrong and then, you know, we did this contour thing. It's a very subtle integral because, yeah.
Yeah, but what I'm saying is, let's say that this 2-point function is obtained by coupling to a source, right?
Right.
Now you couple to that source and you make that source your gauge. It should
Right.
change your answer.
Right.
That tells you that the current is conserved. Right, that's the usual story. That has to work, whatever else works or doesn't work. Right, unless some total derivative or something.
So even with the Chern-Simons plus Maxwell deformation, so is the current going to be given to the same? Is the current given to give you the same expression as the earlier without the deformation?
The Chern-Simons is trying to induce some kind of chirality here, right? Or, oh, I see, that could be a point. No, but you see, I mean, this boundary mass term, we don't have to, you know, if we have this, you know, if you know, to write down the equation of motion, that subtlety doesn't arise, right? So this Chern-Simons term gives rise to both the JZ bar type of currents, okay? And both the things are present, right? Both the sources are present.
Which case are you?
So I'm talking about the Maxwell plus Chern-Simons, right? So in this case, both the sources are present, right?
That's why it sounded like 2 degrees of freedom. But anyway, go on.
Yeah, so, but, the propagator vanishes, that's the thing.
Okay.
So, you can put in both the sources, but one of the propagators, that becomes 0. There are 2, yeah.
Okay, so maybe Omkar is suggesting that I'm identifying the current drop. I was saying that the current is mu JP. And I think Omkar's suggestion is I'm identifying the current drop. Maybe that's
Because there is a boundary contribution from the Chern-Simons term.
Maybe that's it.
Yeah. If you do a gauge transformation,
Yeah.
so it is not invariant up, there's a boundary contribution from there.
The integral was become 2 pi I something.
That is okay. I'm taking small gauge transformations.
Small gauge transformations.
That is not the problem, right? To get Dotha theorem, I don't need some globally not triggered.
Oh, but you're saying the current, but that's like a,
counter terms are maybe violating it. No, but the counter term should be preserved. Maybe a counter. Maybe I'm getting something wrong with your boundary counter term.
so here we are not putting any boundary counter term, right? Or am I? Let's see. So, I mean here this is just a pure bulk calculation, right? The bulk to, let's see.
Yeah. It just sounds physically strange that you have a gauge invariance in the bulk, but not a conserved current. I thought that was not possible. Right? Because just from the following thing, that I can take and couple to pure gauge, and that will just not change anything. And that usually is the argument that tells you have a conserved current.
I have a stupid question, Shaz. So why does the dimension relate to the conservedness of the current? The current needs to be below or anti-below, right?
Below anti-below. Just in any dimension, take J0. All J mu have the same dimension because Lorentz invariance.
Yes.
Now take J0 and integrate. Integrate over a d minus 1 dimensional slice.
Right.
That gives you a charge. Charge is a number with no dimension. Therefore, J had to have dimension d. Same reason that T has dimension d.
D minus 2.
B. But, well, I'm probably not understanding something. But I feel this should be answered. I mean,
No, but I could have missed a minus sign here. That's what, in this reduction, I could have missed a minus sign in the anti-holomorphic, in the H bar. There could be a, I'll check this calculation once more carefully.
Spin becoming non-integer.
Huh?
Then the spin becoming, not one. That's not.
That is right.
it's not so. Yeah, but it is strange, I agree. It is strange. It's not so clear to me that. For instance, once we include the interaction effects with Chern-Simons, every spin becomes non-integer. That's always the case, right?
Yes.
So it's not so obvious to me that.
But the structure,
it's not the same thing.
Yeah, it's not the same. But the structure argument, that I am trying to, this thing, that is very much based on this j equal to 1 thing. If you have other values of j, then it's not guaranteed that you will have this structure.
But what do you mean by j?
J meaning the number of indices, yes.
That is one thing.
Yeah.
But now the question is what representation of SL2R times SL2R is transformed. It's not totally clear that those are the same thing.
Oh. You're saying that, in the
One
boundary.
is a little group kind of thing. I know it sounds like it should be one. But I'm not seeing how to put these things together. If it is 1, then H minus H bar is 1, presumably. If
Yes.
you're saying H minus H bar is 1.
H minus H bar is 1. Let's say we assume that.
Yeah, and
H plus H bar
has to be 1.
Then there is no power, but the power definitely comes. I mean, here there's definitely a non-trivial delta.
The only way those are consistent is H bar is 0.
Yeah, only way these are consistent is this is 2 and this is 4 and this is 2.
Yeah, and that's what you get in Chern-Simons. Right?
That's what I get in Chern-Simons.
Yeah. But so in Youngman's Chern-Simons then sounds to me like since conservation has to be has to be maintained, it must be that H plus H bar as well. Therefore H minus
No,
H bar.
that, yeah. That we definitely don't get. That power is definitely dependent
Or
on the
I'm just saying it
coupling.
totally wrong, but I feel it needs an answer. Because if you're saying that a gauge theory is not dual to conserved current, I thought that was an unusual thing to say.
One question I have, here we are measuring the dimension of J, right? But to see the conformal weights of some operator, you should look at stress tensor OB, right? Not J. Is that wrong?
I'm just looking at the 2-point function of J. That gives you the dimension.
Oh, it's a 2-point function. It's not OB. Oh, okay, fine, yeah.
So, sorry, what did you think about this X being non-arbitrary? Like, if that is the case, then correlation functions of such operators will not be zero. How is this going to be?
Yeah. Well, in Chern-Simons theory, there is it's a different phenomenon. I agree, it looks confusing. I don't have a clear answer. But in Chern-Simons theory, if you took a matter Chern-Simons theory, had it in some charge and coupled to this, then there is a contribution to the spin from the charge field. And that contribution is q squared by 2k. And that is not in general anyway. Okay? From the AdS point of view, I don't know. But from flat space, there's no contradiction. There's no contradiction because now you've got a massive field. Little group is SO2. In every higher dimension, the little group for a massive field is a non-abelian group. And non-abelian group unitary representations are tight. They're labeled by integers. So spin is half integer, integer, blah, blah, blah. Very tight. But exactly
for SO2,
since in quantum mechanics you don't get representations of the group, you get representations of its maximal cover.
Right.
Because projected representation. Exactly SO2, you can have absolutely any
Any value.
value.
Yes.
Because of that's just like saying H and H bar can be arbitrary numbers, they are not restricted.
Exactly.
But finally, when you put them together to get a spectrum of a particular theory, you have to make sure that you keep only those H bar pairs which are mutually local OPs.
That's, this is the discussion we had right at the beginning of the talk. Are we expecting the rules of conformal theory will be modified here? Or are we expecting, to get a novel conformal? So, in flat space, these particles definitely have non-integer spin. Just as particles.
Yes.
Now, their correlation functions appear strange, but you don't worry about that because they're not gauged. Right? Because I'm talking about charge fields. Okay? Once you make something gauged wherein being uncharged, q squared by 2k is 0. And they have nice ordinary. Okay? However, here you are allowing these guys to go to the boundary. Since you're freezing the gauge transformations at the boundary, the fact that they're not gauged well, no problems. It's just that they charge in the global symmetry.
And so you are saying that it is possible that the boundary theory is not like one particular theory, it's not a well-defined theory, it may not give modular invariance here.
Yes, I was saying that maybe that what's happening is that point is something like this, that with the Chern-Simons in the bulk, you get all kinds of anomalies on the boundary. One of the anomalies, for instance, could be for modular invariance. Okay, so it's not really a CFT then. It's locally a CFT, but not globally somehow. And modular invariance being violated is very close to being bouncing to that. Right? So, so that's what I was suggesting right at the beginning of the talk. But I agree that was a meta question. This is some slightly different issue. But would be interesting just to know the following answer. We have areas, Chern-Simons and mass, explicit mass. Just translate that to H and H bar for a representation. Everything that you have is some representation of SL200.
Yes.
Labeled by H and H bar. Just give the translation formula. In terms of mass, so there are two dimensionless quantities, namely mass in units of AdS and Maxwell coupling in units of AdS. So in terms of these two dimensionless quantities, in the end we should have a formula for what? For the representation.
Right.
You've got H and H bar. Would be nice just to have that final answer to stare at. And how it is consistent with the expectation that unless you put in an explicit mass, current should be conserved. I'm not seeing a way of getting that consistent with what you're pointing out, that H minus H bar should also. So I'm confused.
Mhm.
Yeah. Also, you can
Mm.